Today we'll do implicit differentiation. So there are an awful lot of graphs that we just don't really work with very much because they're hard to categorize. Specific relations that are not conic sections like circles and ellipses and hyperbolas, but you get all kinds of, frankly, very interesting looking graphs when you don't have to have a single function defining them. So the graphs of a lot of relations are not functions help well define slopes most of the places. Take, for example, x cubed plus y cubed minus 9xy equals 0. That's this graph. And at most places, we could sketch a tangent line here or there or there. Now, right here, where we come down, it looks to me like it's got a vertical tangent right there. So the dy dx would be undefined. But everywhere else, looks to me like it's got a perfectly good tangent line, so the derivative exists. So when you have one of those, though, try to imagine taking this equation and trying to solve it for y. It's pretty horrible to have to try and do that. You can at least theoretically do it in most cases, but usually it's like ends up being 2 or 3 different functions before you can solve it for y. And it's a lot of work before you start doing any of the calculus. So what we're going to do is find dy dx using what's called implicit differentiation, where what you do is you treat y as some unknown function of x. And then you differentiate both sides of the equation using the chain rule. So let me give you an example here. If y squared is equal to x, that's a sideways parabola. It's 2 different functions. What we're going to do is we're going to treat y as an unknown function of x. Now, I'm going to show you a way to do this that no one ever actually takes the time to write out, okay? And then we'll talk about, okay, we're not going to take the time to write out that, but we'll go, let y be equal to some function of x. I don't know what it is. If I did that, I would have f of x squared is equal to x. So now if I wanted to take the derivative of that, I would have to use the chain rule here, right? So I would have 2 times f of x. So taking the derivative of the outside part, leaving the inside part alone, times the derivative of the inside part, f prime of x, is equal to, the derivative of x is 1. Solving that for f prime of x, we get that f prime of x is 1 over 2 f of x. And you can and are welcome to do this. But mathematicians, being the incredibly, which word shall we use today? Is it lazy or is it efficient? People that they are, decided that's too much to write. I'm going to do exactly the same thing. So every place that I see a y, I'm going to think that is some f of x that I don't know what it is. So I have a composite function because y is some unknown function of x. So when I start taking the derivative, I'll have 2 times whatever that function is times the derivative of that function, which will be dy dx, is equal to 1. Divide both sides by 2y, and we get that dy dx is 1 over 2y. We got the same thing, just a bit less writing. Does that make sense? Jake, you're eyeballing, you're giving it the side eye there. So we're treating y like it is an unknown function of x. So we've got a function raised to the second power. So if we're taking its derivative, we need to use the power rule, leaving the inside part alone, times the derivative of the inside part, dy dx. For some people, it's helpful to every place you have a y, put it in parentheses. Because then it's like, oh, yeah, that's not just y, that's a function. So, for example here, find the slope of the circle, x squared plus y squared equals 25 at the point 3, 4. Okay, so I'm going to take the derivative with respect to x on both sides. So if it just has x in it, I just take the derivative like I normally would. So the derivative of x squared is 2x. Plus, now again, I want to think of this y as some unknown function of x, so I'm going to have to use the chain rule on that. So I'll take the derivative of the outer part, leaving the inner part alone. There'll be 2y to the first times the derivative of y with respect to x, which is dy dx, equals, and here's a place that students frequently go wrong when they first start doing these, the derivative of 25 with respect to x, we're taking the derivative of both sides, is 0. So now we want to solve this for dy dx. So I've got 2y times dy dx is equal to negative 2x. Divide both sides by 2y and we get the dy dx is equal to, because the 2's cancel, a negative x over y. So at the point um, 3, 4, so the slope evaluated at the point 3, 4 is going to be negative 3 over 4. It looks like that. We've got the circle. S squared plus y squared is 25. That's a circle centered at the origin with a radius of 5. And then at the point 3, 4, we can see that the slope is negative 1, 2, 3, and to the right 1, 2, 3, 4, 5. Sorry. 1, 2, 3, 1, 2, 3, 4. Sorry, I miscounted. I was like, wait a minute, that's not right. It's, in my opinion at least, one of the great tragedies that TI calculators decided not to try and be able to graph things that aren't functions. Like, you should at the very least do conic sections. But they don't. Unless you do it piecewise. You have to break it into pieces. And for a circle, it's not all that bad. Even then, it gives you a crummy graph because of the way that it graphs it. On the far right and the far left, the circle almost never gets closed because of the limitations of the number of pixels. All right. So let's show that dy dx is defined at every point on the graph of 2y is equal to x squared plus sine of y. Like, wow, there's a lot going on there. So again, it doesn't hurt to write it so that the y's are offset with parentheses. Again, certainly not a requirement, but every time you see that, I want you to think of, okay, I'm going to use the chain rule here. So the derivative of 2y, well, I just keep the 2, and the derivative of y is dy dx. Equals, on the right side, I'm taking the derivative with respect to x. That matches this variable, so the derivative is just 2x. Plus, when I have a composite function like this, I take the derivative of the outside, leaving the inside alone, times the derivative of the inside. So the derivative of the outside will be cosine, leaving the inside alone, of y, times the derivative of the inside part, which is dy dx. To solve this for dy dx, I'm going to move every term that has dy dx in it to the left side. I could move them all to the right side. It doesn't really matter. I'm going to get 2 dy dx minus cosine of y times dy dx is equal to 2x. If I factor out the dy dx from both of those and divide by 2 minus cosine y, I get that dy dx is 2x over 2 minus cosine of y.
Could you explain how you got rid of dy dx?
I didn't get rid of it. It's right here. So what I did, I know that's not exactly what you were asking, but it is what you said. What I did is I factored out a dy dx. And then divided both sides by 2 minus cosine y. Okay, now cosine of y, well, cosine's defined for anything we put into it. Doesn't matter, so that's okay. The numerator, that's always there, 2x. Doesn't matter what the x is, that's always going to be defined. What's the one potential problem we have if we have a rational function?
It's 0 in the denominator.
A 0 in the denominator. But is 2 minus cosine of y ever going to be equal to 0? Well, no. Because the most cosine could be would be 1. So the least that this could be would be 1. Therefore, dy dx is defined at every point. And I just, it asked me to prove this. I'm going to write out everything that it said. This is called parroting. We do it a lot in AP statistics. You're not sure what to write? Well, write what they said. This is defined at every point on the graph of 2y is equal to x squared plus sine of y. That's what that graph looks like. It's like you were graphing a parabola, but we're kind of shaky. It never quite gets vertical. right? Looks kind of close to it, but never quite gets vertical. So that's okay. So it's got a tangent line everywhere, so it's differentiable everywhere. All right, let's do this one. Find the tangent and the normal to the ellipse x squared minus xy plus y squared is equal to 7. You may not have done many ellipses or any other kind of conic section that had an xy term in it. Most books kind of ignore those unless you're doing an advanced sort of class. What it does is it takes the figure and it rotates it. All right, so we're going to take the derivative with respect to x. I'm just going to go in here and go, okay, remind myself to do the chain rule on everything that's not an x, any variable that's not an x. So taking the derivative of x squared is just 2x. Minus, I have a product, so I must do the product rule. So that'll be the first factor, x, times the derivative of the second factor, so that's dy dx, plus the second factor, y, times the derivative of the first factor, the derivative of x is just 1. Plus the derivative of y squared, that's a composite function. So I'm going to have 2 times the inner function left alone, so 2 times y, times dy dx. And then the derivative of 7 is 0. No matter what variable you're taking the derivative with respect to. So let's go ahead and distribute the negative and gather up the dy dx's. So I'm going to have 2x minus x dy dx plus y plus 2y dy dx. Because of the things that are positive, I'm going to leave the things that don't have the dy dx on the left side and move everything that does have a dy dx to the right side. So that'll be a 2x plus y is equal to, and I'm going to go ahead and factor out the dy dx, x minus 2y dy dx. So then that's 2x plus y over x minus 2y is dy dx. So then at the point negative 1, 2, that's going to be negative 2 plus 2 over negative 1 minus 4 is equal to 0 equals the slope of the tangent at negative 1, 2. So the slope of the normal at negative 1, 2 will be undefined. So the graph for if I have a slope of 0, if you have a slope of 0, the x is changing all the time, but the y never changes. So the equation is y is equal to 2. And the normal If I have an undefined slope, the y is always changing, but the x is not, and the x value is x is -1. And that, well, what have I done wrong here? Hang on just a second, because that's not at all right. Ah, classic mistake. Did you see it? I forgot to distribute the negative sign here. That's minus y. So then it's not 0. So it's -4 over -5 is 4/5. So we've got y is equal to 2 plus 4/5 of x plus 1. And the slope of the normal then will be -5/4. So our equation be y is equal to 2 minus 5/4 times x plus 1. Yeah, that looks better. Two things to point out here. One is that the mistake that I made, and I did not make it on purpose, but it does point something out. When I do these problems, I usually think about it this way, as x squared plus -x times y plus y squared is equal to 7. The reason I think about it that way is then I don't have to distribute the negative sign, and I don't make that mistake. A second thing to think about is as soon as you have taken the derivative, you can go ahead and substitute in the point x is -1 and y is 2, and then there's less algebra work to do. And I strongly suggest that you do that also. That once you've taken the derivative, go ahead and substitute in -1 for x and 2 for y, and now the only unknown in the whole thing will be dy dx, making that faster and easier to solve for. So let's do the second derivative for this, d squared y dx squared, and I'm going to add on an instruction that's almost always on there in terms of x and y. You'll see why that's important in just a second. So again, I'm going to offset the y in parentheses. So this would be 6x squared minus 6 times y to the first times dy dx is equal to 0. Although you don't absolutely have to, I think it's a lot easier if you solve this for dy dx. So I'll have negative 6y dy dx is equal to negative 6x squared. Dividing both sides by negative 6y gives me that dy dx is x squared over y. Now I'll take the derivative with respect to x again. So I have d squared y over dx squared is equal to, and I have to use the quotient rule, so I'm going to have the denominator y times the derivative of the numerator, 2x, minus the numerator, x squared, times the derivative of the denominator. Remember, the denominator is y, which is some function of x, so that is dy dx. All over y squared. And this is why the in terms of x and y is important, because if it didn't say that, you'd be welcome to leave it like this. But substituting x squared over y in place of the dy dx, we get 2xy minus x squared times x squared over y all over y squared. This is a complex fraction, and therefore I need to multiply by the denominator that's giving me the troubles, that is the y, so I multiply both numerator and denominator by y. And that's going to give me 2xy squared minus x to the fourth all over y cubed. Occasionally on these, they get cute with you, and when you get to either dy dx or the second derivative, they go back to the original and go, oh, you know, you could simplify this by taking the original, messing with it a little bit, substituting it into this, and you're like, oh, all these terms drop out. Yeah. That'll happen on some of your homework problems. I doubt that you'll ever see anything like that on the AP exam. But they do occasionally, so I always look back and go, is there anything where I could? And, you know, you could solve this for y squared and substitute in what you get into here. I don't think it's going to make it any better, but occasionally it does. Okay? Any questions? All right. So that's implicit differentiation.